Well, I had a request recently to do a tutorial on how to work with a genetic algorithm. I did my dissertation on a topic that used genetic algorithms for optimization. And so I thought I would just make this video, which turned out to be a lot longer than I expected. But hopefully I'll be able to go over everything, sort of nuts and bolts, from the very beginning to the very end to give you an idea of how this whole thing works and how you might use genetic algorithms in the work that you do. So I'm starting out with a fresh build, as if I don't have anything installed at all. Now, full disclosure, I'm not a Python programmer here. I have Python 2 installed on my computer, but here I'm downloading Python 3. They're basically the same. There are some slight differences. But for the purposes of what we're going to do today, I'm going to try and leave everything in and only speed up the stuff that is really repetitive. So by way of introduction, while Anaconda is downloading here, genetic algorithm is basically a way to optimize some process, right? So in this particular example, we're going to optimize the route that you take between two locations, and we're just going to use all strictly simulated data, and I'll describe to you how I'm going to formulate this problem. But we're going to use a genetic algorithm to basically find the fastest route between two places. Now, this may or may not be the way that you'd actually want to solve this problem if you were doing something like, say, Google does with Google Maps or Apple Maps or whatever. So I'm certainly not contesting or stating that this is the kind of optimal solution to this problem, but it is an interesting one, and it'll certainly give us a chance to go through the process of going through a genetic algorithm. So how are we going to frame this problem? What we're going to do is we're going to define a network that is going to represent the locations on our map. So if you imagine a network of, say, friends, right? So each person is represented by a dot, and then you draw a line between those dots if the two people are acquainted with one another, or if they're friends, say. In network analysis, that's called an adjacency matrix, and it's a clever way to pose this problem. So in this case, we are going to treat intersections as nodes in a network, and roads as the lines between those dots, those nodes, as roads, right? And so you can think of a map as a giant network, and what you can do is you can actually take that network and you can display it as a matrix. A symmetric matrix, actually, where you have n rows and columns. It's a square matrix, and each value represents the distance between each intersection. Right, so from intersection A to intersection B, that is going to be the AB point in the matrix. So row A, column B. And the number there is going to tell you how far it is from A to B, right? So that is how we're going to frame this problem. And so the distance between A and B is the same as the distance between B and A, and so that's why the matrix is symmetrical. And just for the purposes of this problem, we are going to set equal to 0 in that matrix any two intersections that aren't connected with one another. So that's lots of intersections. You can't get to every intersection from every other intersection directly. And so any intersection that doesn't directly connect with a road to another intersection, we are going to label with 0. And we'll just treat those as sort of not connected. Right? That's how we're going to frame the problem. The other thing that we need to do is to be able to frame a route from one location to another location. And we're going to do that by going from intersection to intersection, which is not strictly speaking what you would necessarily want to do because your typical destination and starting points are not intersections. But it's close enough, right? So in this case, we're going to have just a vector, just a column of numbers that correspond to a particular intersection. So if you had a vector that said 0, 1, 2, 3, then you would go from intersection 0 to intersection 1 to intersection 2 to intersection 3. And in that way, you can take a single column of numbers and you can use that to define a route through your map. And really, those are the only two things that we need in order to frame this problem and to use a genetic algorithm to solve it. So now what we have installed is Anaconda Python, which is just a distribution of Python that includes some really handy mathematical frameworks and modeling frameworks and so on. And we're going to start up a Jupyter notebook just by going to the folder where we need to go. And we are going to type in Jupyter notebook into the command line, and that's going to open up in our web browser this Jupyter notebook here, where we'll be able to type in and execute code in this kind of cool notebook, this development environment. So I'm just going to go through and create all the separate functions that we're going to need just as shells for the purposes of what we're doing today. And you'll have to forgive me, my Python's a little bit rusty, so I'm going to be Googling a bit, and I'm going to try and leave that in, though I am going to speed it up throughout this process so that we can get to where we need to go a little bit faster. I think from start to finish that this project took me about 5 hours from the time I started downloading Anaconda Python to when I finished the recording and started the editing process. So about 5 hours spent. It was a fun Saturday morning. My wife thinks I'm crazy, but hey, there you go. That's what I love. So what are the functions that we need? I suppose I should first start out by describing to you how the genetic algorithm actually works. There's lots of really good tutorials out there on the internet and good descriptions, but let me just see if I can summarize it for you. The basic idea is that you want to be able to have a population of solutions. So the genetic algorithm is kind of a metaphor, right? So it's a metaphor for the way that natural selection happens, right? So if you have a population of sheep and you only allow the healthiest, strongest sheep to breed, then your population of sheep is going to get healthier and stronger and better. Whereas if you only were to allow, say, the weakest and scrawniest sheep to breed, then it would get worse and worse and worse. So the idea with the genetic algorithm is that you're going to start out with kind of a random population of possible solutions. And so the function that you see there, CreateNewMember, is a function that's just going to create a random but valid solution to the problem. So starting at 0 on our map and ending at the last element on our map. So if it's 100 different intersections, then we're going to try to go from 0 to 100. We're going to simulate this data. So we're going to simulate a population of random solutions to our problem, and then we're going to let them breed with each other. And we're going to let them breed in the sense of the ones that are the best solutions get to breed with other good solutions as well. And solutions that don't work very well, solutions that take a very long distance, those are going to be ones that are less likely to have the chance to pass into future generations. And so throughout that process, we are going to hopefully see our population get better and better at navigating the map from 0 to 100. And by the end of this process, we will hopefully have a good solution to the problem. Now, the one thing that you'll notice here is that we're not by any means guaranteeing a perfect solution to the problem, right? So we're not saying that once you're done running this thing that you're going to have the absolute optimal solution to the problem. The thing about the genetic algorithm is it's going to give you a good solution, but you're not guaranteed that it's the best one that you could possibly have. And so we're just going to have to live with that as we do this project here. So the procedure for the genetic algorithm is to start with a random population. And then what we're going to do is we're going to run through a round of breeding, which is going to let our best possible solutions sort of intermingle with our other good solutions and produce some offspring. And then we're going to do that for a certain number of couples, right? And then we're going to generate some more random solutions. So we want to keep adding new interesting ideas into the pool. And then the last thing we're going to do is we're going to do some mutations, right? So we're going to throw in some random changes to these solutions in order to get some noise in there, so we don't get stuck on a solution that's good, but maybe not great, right? So we're going to constantly be throwing noise into this process so that we can get to a good result. So that's the basic process that we're going to go through. So what are these different procedures that I'm writing here? So the one that I'm working on now is called Initialize. That is the procedure that is going to draw the map. So I'm going to randomly simulate that adjacency matrix, that matrix that is going to contain all of the information about how far my intersections are from each other. The second function there is a function called fitness. And what that's going to do is basically just calculate the distance of a route. Right, so it's going to say, okay, you're starting at point 0 and you're ending at point, say, 100 if there are 100 intersections. How far was it? Right, so it's going to use the adjacency matrix to calculate the length of the route. Because in this process, we're trying to minimize the length of the route in order to find the best solution. Here, best means shortest. Okay. The next one is called crossover. Crossover is what they call it when you take two solutions and you breed them. And the way that we're going to do that is we're essentially going to take a piece of one solution and another piece of another solution, and we're going to mix them, right? So we might, if we had a route that was, say, maybe route A is 10 elements long and route B is 8 elements long, then we might take the first 3 elements of A and the last 6 elements of B, and have that be a new solution. And then we're going to take the first 5 elements of B and the last 2 elements of A, and that's going to produce a second solution, right? So we're kind of mixing and matching. We're taking good solutions, and we're grabbing a bit from one and a bit from the other, and we're using those to produce new solutions in the hope that the offspring will be good solutions to this problem. Mutate is a function that is the one that we're going to use to introduce random noise into this process. So mutate is basically just going to say, if we're going to use a random number generator, and if you're past a certain threshold, then we're going to make you turn a different direction, right? So you're going to go down a different path at a certain point in a route. The mutation rate in this particular case is going to be pretty small. I think I set it at 5%. But I made it a parameter, so you can adjust it and try to optimize it to get to a good result faster. But the mutation rate is basically just a way to say, okay, let's turn a different direction. Let's do something different in order to find a good solution. Okay, CreateNewMember is the next one. CreateNewMember is basically a function that is going to create a random member of the population. So we're going to use this to start with and as we go throughout this process. And create next generation is just going to run a loop in order to create a certain number of new members of the population. The last one, called main, is just the main body of the program. Now, I'm starting with initialize here, and n is the number of intersections here in my process. And I'm just going to loop through n a couple of times because I'm creating a square matrix. I'm calling it map. I actually end up changing the name to the map because map is a special keyword in Python, and I don't like using them. So I realized that in just a few minutes here and change it to the map. So you'll see that happen in just a second. But you can see for I in n and for j in n, I'm basically just looping through the different elements of the adjacency matrix. And here I'm realizing that my syntax is wrong, and so I actually have to go and look up the range function for Python, which is humiliating, but I left it in because I believe in transparency here. So you have to use this range function. I jump from language to language, and I can never remember the syntax for these things offhand. So here we're going to loop from 0 to n through both I and j. Only for j, we're not actually going to loop through n. Remember, the matrix is symmetric. So we're actually going to loop through 0 to I. Now, this is a bug that I fixed later. It should be 0 through I. The range function is not inclusive, right? So it's not going to include that last value. So it actually needs to go 0 through I. But the reason I can do that is because this matrix is symmetric, and I'm actually going to just copy the matrix, the bottom half onto the top half here. And so I only have to run through half of it. And here's me trying to figure out how to generate random numbers. Part of the genetic algorithm means a lot of random number generation, both uniform values between 0 and 1 and random integers. So we're going to have to do both of those things. I end up using random. Go figure, it's very aptly named. And also NumPy, so got to import NumPy. It turns out that using vectors and arrays that are NumPy arrays is much more convenient than using lists in Python a lot of the time. So that's what's going on here. One of the parameters for the initialize method is probability of 0. So I want to be able to control how sparsely the map is, or how sparsely connected the map is. And so I create a parameter called P0, where when I generate a random uniform value, if it is less than that value, then I'm going to set that value equal to 0. And if it's greater than that value, then I'm going to assign it some random number. I start out with that random number being a large number, a number between 0 and 100. I ended up changing that so that it's between 0 and 1, just so that the final values would be smaller. I don't know that that's really necessary, but I ended up doing it later as a part of trying to figure out a pesky bug. I don't think it had any bearing on the final result, but I did end up doing it. And here you see me starting to just do a quick test on the initialize parameter or initialize method. And you can see here that I've made a silly error. And so I'm going to go through and just debug that until I finally get it working. I actually end up simplifying this a fair bit. It turns out this is absurdly complex. I end up just initializing the entire matrix with zeros and then going in and changing those where I need them. And so it is working here, but I go in and fix it up and make it a bit more efficient here, and I'll just speed that up. You can see here the 4x4 map here that I've made. You'll notice the diagonal is all zeros. That's because the diagonal corresponds with staying put, and I don't want to call that out. And then there are some other zeros that are interspersed within, and some positive values that indicate the distances between the arrays, the intersections. Now I'm going to start working on the CreateNewMember method. That method is just going to create a new root, and this one actually takes a little bit of work because I wasn't really thinking about it right at the start. I started out just creating sort of random vectors, right? But it turns out that I need those vectors to be valid solutions to the problem. So I need the vectors to start with 0, to end with the last intersection, and to follow a route that doesn't hit any zeros on the map. And so I go through a whole bunch of different iterations here before I realize that. And then I actually go in and fix it and actually make it work correctly. So I'm gonna speed up a lot of that here because there's 5 hours of footage here. This next little bit is writing a small piece of code that's just going to loop through that CreateNewMembers function and just create the entire starting population. It is at this point when I start writing the fitness function that I realize that I've made an error in the way I'm creating the population, each new member, that I haven't actually made a way for them to be valid, so that every member that I create represents a random but valid route from the start to the finish. And so I jump down to the CreateNewMember function, and I start adding some complexity that really has to satisfy 2 conditions. One is it can't pass through any zeros in your adjacency matrix, and the other is that it has to end in the on the final point, right? So the first point has to be 0, and the last point has to be n, where n is the number of intersections in the map. So I start trying to generate some complexity where I'm generating a population of or routes of fixed length, right? A fixed number of intersections that also satisfy both of those conditions. In the end, the way I ended up creating each new member was essentially to start at 0 and then create a list of all the unique possibilities that you could go to. So essentially all the places that 0 connected to, and then I'd choose one of those at random. And then I would go to the next point and find all the available options and choose one of those at random. So I knew the path that I was taking would always be valid. And then I just kept going until I ended up at the final point. So it's just a simple random walk through the network. And that's the obvious way to do it. And it took me about an hour to get there over a pretty simple piece of code. So I've left it all in, but I am speeding it up so that my humiliation isn't too intense. So you can see here in the final version of the code, I'm basically running a loop where I'm just going to keep going until I hit that final point. I'm going to start out with a list of all the possible values, and then I'm going to randomly select one of those possible values and append that onto the root so that I'm always following a valid path. And then when I hit that final value, then I'm going to go on to the next member. Then I start working on the function that'll actually calculate the distance between your starting point and your ending point that you travel on the route. It turns out this is pretty straightforward. It's just a matter of summing up the different vertices that you pass through on the way to where you're finally going. So this piece is very straightforward. The basic idea here is that you're going to initialize your final score to 0, and then you're going to loop through all of the elements of your route and just add on to whatever that score. You're going to keep a running tally, starting with the first data point, not the second one, obviously, because that is at 0. And you're just going to add on the value of your distance that you're getting from your map onto that value till you get to the very end. Very simple. Here's where I make the second mistake. There are really two big mistakes, both very stupid. We just went over the first one. And the second one has to do with copying of arrays and lists and so on in Python. As it turns out, when you set one array equal to another array, that you are actually just referring to the place where that array is stored. And so you're not actually making a copy of it. And I knew this, but for some reason it didn't ring home. So there are a couple of places here where I set one slice of a array equal to a new value and expect it to make a copy, and it doesn't. And I don't realize that for a while. So I end up going through here eventually and changing some of these assignment operations to deep copies using copy. And so you'll see that come through in a minute here. But for the crossover step, basically what I'm doing is I am going through a couple of different methods of doing this because it was just hard to get it working right. The main problem being that that deep copy issue, which I didn't realize for quite some time. But the basic idea here is that I want to find a cut point in each one of the members that I'm breeding together. So the crossover is the breeding step. And so I'm finding a cut point in the first member, A, and the second member, B, and I'm swapping them, right? So I'm taking the first half of A and attaching to it the second half of B, and the first half of B and the second half of A, and attaching those. And that's how you breed them together. But there is one more mistake that I've made here. When I do that crossover, I need to guarantee that the resulting children are valid roots. And I don't realize that for a little while here in this process. And so what I end up having to do is make sure that I'm crossing over only at the same value. So let's say that I pass through, intersection 43 in population A, and I also pass through intersection 43 in route B, then that is one possible option for doing that crossover. And so in this crossover step, what I end up doing is forcing it to cross over at places where they share a common intersection. So you can almost imagine two paths that are starting at different places and they cross each other. And at that point, I'm just switching them, right? So I'm just crossing them over at places where they already intersect. And that turned out to work really well. made it really easy to do the crossover, but it took me a while to realize that I needed to do something special in order to keep these roots valid. And so that's what this is all about here. It's actually about right here that I finished the first version of this crossover method, and haven't yet realized that the resulting children are not going to be valid solutions. And so I leave this here, and I'll come back to it shortly and fix it once I realize what I've done. What I move on to now is the mutate section. Mutate's pretty straightforward. I'm basically just setting a threshold, so I pass into the mutate function a member, a root, I'm calling it, and a probability, right? So some threshold. In this case, I think I set it to 5% down in the main body of the program. But in this function, I'm basically just going to generate a random number, and if it is less than that probability, then I'm going to go ahead and do a mutation, and that is I'm just going to re-roll the rest of the path that you're walking down. And so that's all I'm really accomplishing here with the mutate function. And now I start working on the main body of the program. This is the thing that's going to sort of orchestrate all the different pieces. And so I've been going about this for a while now. And so I'm getting a chance to start actually making things happen and realizing that nothing is really working. I'm going through here and just making a quick outline of what I plan to do. First thing is to initialize the map and create it. Second is to create the starting population from random. Those are the functions I've already written. The third is to loop through, basically create a large number of iterations where I evaluate the fitness of each member of the population, and then allow those members of the population to breed, mutate them, and repeat that for a certain number of iterations until I'm happy with the result. The nice thing about creating the program this way, breaking it down into little sub-functions, is that now writing the main body of the program is just as simple as calling all the functions that I've already written. So I start out this section here by just initializing some parameters. There are some things that I need to set. Things like, for example, what proportion of zeros I want in the map. Also, how big the map is going to be, how many intersections there are. I'm also going to set the size of the population. That's the next thing. And the next bit is creating the population. So I'll just loop through and inside that function and just call them. You see me here doing some renaming here, changing of the parameters a bit. I'm just mostly fiddling with it to get it so that everything is consistent. So I'm not passing the size of the map, instead I'm passing the map itself. Just consistency. And then what I do here is just start a loop. This is what I'm going to iterate through. I realize along the way that I need to create a few additional functions. For example, I don't have a function here to create or to score the entire population. So I'm going to just write a quick function here that's going to take the whole population and loop through it and just call that fitness function so that I can return a vector of scores to the main body of the program. Okay, so I realize here that I need another function, and that is the function for choosing which members of the population get to breed. I call it pick pair to breed here. I actually rename it later because I hate the word breed. I think I call it PickMates or pick partners or something like that a little bit later. So you'll see me rename it, and it's just for aesthetic reasons. What this function does is it's basically going to look at the scores that you get from the score population function. And what it's going to do is it's going to essentially choose the roots in the population that get to advance to the next round, that get to cross over. And those are going to be passed into that crossover function that we wrote a little bit earlier. I do this a variety of ways and actually end up messing it up a couple of times. Turns out that we're minimizing the distance here, and the way I write it actually benefits the longer distance. So I actually try to find the longest possible route to the end for a long time, and I don't realize that till nearly the very end. So I write this wrong at first, And I'm just going to speed that little bit up here so that you can see how stupid I am. And then at the end, when I realize it and fix it, then I will point that out. Now that I have the PickMates function written, which weirdly I changed to PickBreeders, which I hate even more, and I changed that later for aesthetic reasons, of course. I'm going to use that crossover function and essentially mate the two that get selected. There is some randomness involved, as you saw, and that function returns a tuple, which I'm assigning to new1 and new2, and then I'll just add those to the new population. Here I am initializing it, and then I will just add it. Number of couples is the time or the number of breeding pairs that go into the next generation. That's a parameter that I created up at the top. I think I go back and forth a bit in terms of which ones are parameters and which ones aren't, and so on. So you'll see that change a little bit, but you get the idea. We're choosing the number of pairs we want to find, and then we're adding that to the population. The next step here is to create those members of the population that are going to be randomly created. So I'm going to introduce sort of the new blood into each population or into each generation, and I'm just going to add those guys in a certain fixed number to each generation each time. And then the next part is to mutate. So I'm just going to call that mutation function. I end up having to create a parameter that I'm going to pass in. That's the probability of a mutation. I didn't really play with this to see how larger and smaller values of mutate probability change the performance of the algorithm. So I think that's definitely something worth exploring. I set it for 5% here and never change it. But I recall that in my dissertation, starting out with a high value and then changing it as you go forward can really improve the performance of the algorithm. Having dynamic values of that probability is a good way to tune it. And now you can see where it says population equals new population. That mistake there cost me like an hour of time looking for the problem. Of course, what's happening here is I'm just creating another reference to the same matrix or the same array instead of actually making a copy of it. And that turned out to be a mistake, obviously, and it took me a while to realize it like a dummy. But I finally did and finally fixed it. You can see it there glaring at us back and sort of mocking me from the distance. And now begins a pretty long process of debugging. Now that I've gotten all the pieces written and the main kind of skeleton of the program put together, then now all that remains is to run it a bunch of times and see if it gives you what you want. And certainly in this case, it didn't. So I had to spend some time getting it working like it's supposed to. The main thing that I'm doing here is trying to get that crossover method working right and the scoring working correctly. I haven't yet realized that I'm maximizing instead of minimizing, and so I'm wondering what in the world is going on here. Here's one piece that I haven't mentioned that I should have. Whenever you run your genetic algorithm, you want to keep some of the best performers from the previous generation. So you'll realize if you think about it that the way I had it set up, there wasn't a way for somebody to make it through from one generation to the next. And that meant that your result, your solution wasn't necessarily monotonic. In other words, it could go down and up and down and up. And it would tend towards the right answer, but it was unpredictable. And so this section of code here is just to add some good folks, some good roots from each generation into the following generation, so that you always maintain at least a monotonic result. I'm just blazing through this little bit of code here just because I'm basically searching for the issues, right? Because it's not working right. I'm getting invalid solutions. Things are going crazy, and that's because I've got this deep copy problem and a couple of other issues going on. So I'm just going to skip through the details of this code because it's basically just debugging, and I'll have all this code out somewhere on GitHub that I can link to in case anybody's interested. And this is the part where I realize that I've made a mistake, and I need to make sure that the crossover happens at an intersection point so that the solutions remain valid, right? So that I don't create errors and issues in this process. So this is a conceptual error rather than a coding error, which is certainly worse, but in the end we found it. So here you go. And this process took about an hour, which I've condensed down into just a few seconds. So now for the fun part. Once you have the code actually working, and I believe that it is at this point, there are a few minor bugs that I sort out in the process here. But now I need to visualize everything. So I can see that the distance actually decreases and the number of jumps tends to decrease, although those aren't necessarily the same thing with the way this problem is framed. Now I need to visualize it. So I'm going to draw little heat maps of the adjacency matrix. So those are going to be basically darker colors or lower values. So you can see that diagonal there is zeros, and there are zeros kind of dotted throughout, and then lighter colors are higher numbers, right? And so what I want to do here is basically trace on the adjacency matrix the path that the root takes. And so what we should see is that it becomes less meandering over time. And in fact, that is what we see. My main problem here is that I'm not exactly an expert in matplotlib, which is what I end up using here for these visualizations, but I get there in the end. So here's what the visualizations look like. Black dots here represent very small distances. You can see the diagonal is entirely black from the top left to the bottom right. Those are zeros, and you can see the different zeros across the plot. Those are places that can't be connected directly. But you can see the initial pass from the algorithm is a bit wandering. There's 1, 2, 3, 4, 5 points on the plot. And this is what it looks like on the first iteration. And the second. And the 9th. And the 29th. And the 32nd iteration. And the 141st. And even though the patterns seem to get maybe more complex and the number of points goes up or down, the overall distance is what's being minimized, and it is decreasing throughout this process. The dots that the white dots are on are getting darker. Now, I played with this a fair bit, and what I ended up deciding to do is actually make a slightly different, more complex version of the map that will allow me to reduce the number of points that are connected. I could do that by reducing or increasing the number of zeros in the overall map, but I wanted to add a little bit of structure to it. Basically create sections that were interconnected that weren't connected with other parts of the map. And so this more complex map is basically just going to introduce groups so that I can take and make maps that look like this. This map has 100 intersections, and this one has 1,000 intersections. And you can get some really cool stuff to come out, some really fun designs, and it's neat to see how they simplify as the algorithm progresses. This particular plot started out with a 1,000 by 1,000 grid, so 1,000 intersections, and I had 95% zeros here, so it's very sparse, and you can see how it simplifies pretty quickly using the GA. This is about 70 iterations to get here. So I'll put a link in the description to this code. I hope this was useful. It's a much longer video than I usually do, but it's pretty detailed, and I wanted to be thorough in terms of what I showed as far as the actual process of going through all this coding here. But pretty cool to code it up from scratch in about 5 hours as kind of a I'm not an expert or an engineer or anything like that. So that was pretty exciting. If you like this video, leave me a comment, and I'd love to hear about it. Subscribe, share it with your friends, and I'll see you next time.